Hi, I'm Domniki Asimaki. I'm a faculty at Caltech. I did my PhD at MIT. First of all, thank you for the invitation. It's a pleasure to be back at GEER-NCREE and in Taiwan. I was here last year as a team lead for GEER, and we did a joint GEER-NCREE reconnaissance of the Chihshang earthquake sequence. The purpose of the reconnaissance was for us, the US team, to take some lessons learned back home. The reconnaissance was primarily led by GEER-NCREE. They basically escorted us to the various places, and then we tried to understand some things that we were seeing. And then back home now we're trying to interpret the things that we saw. So a lot of the things that people from Taiwan will see in my presentation are probably, they have seen them several times, but for the US members in the audience, I have a few maybe new results to show. And some exciting things that I've been learning about the tectonic setting in the longitudinal valley that I am excited to share. So bear with me for the things that you've already seen. The no GEER reconnaissance is an island. The US team was led by myself and Ben Mason. And we had a bunch of people. The main members were Brian Gray from LETIS, who led the fault rupture observations, my postdoc, Greg Lavrediadis, who thereafter has been processing the ground motion records that GEER-NCREE helped us obtain. Trevor Carey from the University of British Columbia, who did the observations from the bridges. And then a bunch of other people from different places who did some site characterization and tried to find landslides, but couldn't quite do so. Not for lack of effort, I may say. The GEER-NCREE team, I'm sure I forgot several people who helped us, but sincere thanks to Director Chu and Deputy Director Wu. And also, we had the team of Professor Wang from Chinan University, who brought a bunch of different drones and followed us to places that were of interest. And you will see some fantastic three-dimensional models that we currently use to build three-dimensional finite element models and try to shake them numerically. For those of you not familiar with GEER, this is a National Science Foundation supported organization that is intended to support researchers, senior, not so senior, junior, and students to travel around the world and observe the outcomes of natural experiments of natural hazards. The intent is for us to learn and bring back understanding and case studies, and then communicate that to our communities and to our students, and ultimately find ways to translate that into our improved code provisions. And this is a long list of the things that GEER does or is supposed to be doing. Okay, so the context of this earthquake, Carrie C, by the way, asked me why would GEER be interested in this baby earthquake. So I'll try to tell you a little bit about why. So the Chihshang earthquake sequence was took place on the 18th of September of 2022, and it was preceded the day before by a strong foreshock. And it was originally believed that it occurred on the active longitudinal valley fault, but subsequently the moment tensor solutions showed that the event actually was triggered on the less active central range fault. And And there are two papers I will refer to. Both are on Nature, and one is as recent as, I think, 6 days ago. And they show that the event was started on the Central Range Fault and eventually dynamically triggered the longitudinal valley fault near the north part of the suture. For those of you, again, less familiar with the tectonic setting, as I was up until maybe a month ago, no, maybe less, a little more than that, the longitudinal valley fault is the suture between the Filipino Sea Plate and the Eurasian Plate. And it's about 500 kilometers length by 7, roughly. And so it accommodates 8 centimeters of convergence a year. And the Central Range Fault had been believed to be there. There were several publications primarily led by Bruscio and in 2007 and thereafter. But it was primarily blind down here in the southern part, south of Yuli. And in point of fact, had been quiescent for the most part since the early 1900s. And as a consequence of that, it didn't appear in the seismic hazard in the active fault map of Taiwan that was published in 2021. So it was believed to be there, but it was not considered to be an active fault. The major hazard producing fault in the region was the longitudinal valley fault. And so the event, that's why the event happened, was initially attributed to the longitudinal valley fault. And this event basically proved not only the existence of the Central Valley Fault, but also the fact that the two faults are coupled in moment budget over time. And they're basically talking to each other, and they not only dynamically during the rupture, so the Central Valley Fault ruptured and then ultimately triggered dynamically the longitudinal valley fault. And I'm looking at Professor Ma, who can yell at me when I eventually make a huge mistake by trying to explain what I understood. But also over time, the recent paper was published by, it was Tang et al., right? And it was Bruscio was one of the authors. Shows that the quiescent period of the Central Range Fault was primarily because the longitudinal valley fault was producing earthquakes, and it was basically over time that the moment budget of the two faults should be accounted together. So when one is working, the other one is not creeping and appears to be inactive, and then the other one is activated, and the first one can take a break, and so on and so forth. And that means a lot, at least to me, seems a very, very, very interesting problem in terms of hazard in the area, having two faults that are meeting at opposite angles in the middle of the longitudinal valley, and they have different times at which are activated, but they basically shake the same region. That as a precursor to what I'm about to say, and then I'll tell you more about why that matters. So the reason why we deployed a team, and was because I love Taiwan, but that's not necessarily that strong argument. It was, we had 30 records at a distance less than 25 kilometers from the rupture. And as people with experience in ground motions know that's not very often the case, to have a lot of records in the very near field. So we wanted to see A, the effects, and B, the effects of those strong motions on the structure. And because the valley is very narrow, I was very excited about potential basin effects, which we didn't particularly see, but what we saw were a series of bridges that crossed the longitudinal valley, and a very clear directivity effect going north. So we saw the progressive failure of bridges crossing the same normal to a fault as the rupture propagating north, and how the interaction between the pulses and the bridges led to the catastrophic or not failure of those structures. And so we wanted to look at the surface expression of the rupture and whether it was localized or distributed, and try to understand why and where that happened. The interaction between the fault, not only the bridges, but also structures. We were hoping to see landslides, but we didn't. The ones we saw were triggered subsequently by rainfall. They could potentially have been loosened by the earthquake and then triggered by rainfall, right? But that's something that we couldn't have known at the time that we arrived. And we did see very few, if any, manifestations of liquefaction, although there is the loose sediments in the middle of the valley with relatively high water table. So we were, and damaged bridges, we were confident there would be abundance of liquefaction. And Chihshang, I don't know if he's here, where he is. I look forward to his talk. I suspect there wasn't enough duration. Like we looked and looked and looked, and where was the liquefaction? Not everywhere. So the team of GEER-NCREE and we deployed 3 groups of people organized by the interests of the main interests of our group. One studied the bridge failure, the other one followed the fault rupture, and the third looked for landslides but didn't find many. And we sort of rotated around, try to learn from everything. We had more senior people on and more junior faculty and younger staff. So the outline of my presentation, and I have no equations, I think, and I have lots of pictures, so enjoy. So the surface rupture approach that we followed, because of the extensive expertise of the Taiwanese geologists, geomorphologists, seismologists, we weren't trying to duplicate anything, we were just trying to learn, so we focused mainly on the engineering aspects of the rupture, and we primarily focused on the longitudinal valley fault, so it triggered rupture effects rather than the main strand of the central range fault. The rupture structure interaction, and we looked at differences between the distribution, the narrow distribution and more distributed rupture zones. And we had I think, one of the very few opportunities to see repeated ruptures in a very, very narrow zone of several earthquakes. And I'll show you in a minute. So 3 examples. The first one, let me show you here. So now I can walk. So the first angle is Fuli, Dongli, and then Yuli is further up there. And Professor Ma joined us in the reconnaissance. So Fuli, the rupture was confined in a very narrow zone, probably less than 10 meters wide. The deformation was primarily left lateral, and at places purely strike slip. And the position was well defined by the existing geomorphology, so it wasn't very hard to find where the fault was, except when there were restrained bends the fault, or potentially because of the built environment. And the displacements were on the order of several centimeters. This is a high-resolution picture that my colleague Brian Gray took, where you see a finite element model of a real structure with a little pavement here, and every single piece of the pavement had moved by a little bit, so we're able to measure the strain distribution of the fault zone. In the total about 60 centimeters, plus or minus 5. Looking at the cross-section of road 23 right here, the elderly owner of this poorhouse had this part repaired in the earthquakes of 1951, 2003, and in March 2022, the same exact part. The main expression of the 22 September earthquake happened right across. This was almost purely strike slip. And then there was an apparent restrained bend of the fault that disappeared below the structures and caused extensive damage to structures up there. This picture, I should probably use this guy, right? So this picture here is taken from this location, and you can see from the pavement the expression of the fault zone is just purely localized on the order of 20 centimeters, and once the fault bends and disappears below the house, then it emerges as a pop-up, basically, where the foundation of this structure, the fault went around the foundation, right? Path of least resistance. It wouldn't bother to break the concrete, but it popped the foundation up, and it caused 14 centimeters extension upwards, this heave, like you can also see here. Looking from, that's one block south, looking from this point towards the brick wall. This is the projection of the fault, and you can see the projection of the fault, and you can see the offset. That's about 90 centimeters, although we didn't necessarily know that that was exactly the entire displacement was coseismic. That it could have been creep. After all, it took us a month to get there, accounting for collecting all the team and quarantining and all that. And these are cracks right here. The blue lines correspond to cracking, and the red is our projecting estimate of the fault line. A really neat strain meter that we identified, we were pretty excited, was the rice field. And because each rice field line is 25 centimeters, so if you count the displacement of the rice fields, we could actually measure directly. And that's Brian Gray put this picture together. So that was 50 centimeter offset, and that you can just count the number of rice lines that the picture was offset, and you could measure exactly the amount of offset of the displacement. Now, halfway between Yuli and Fuli, about 10 kilometers north from Fuli, is Dongli, and there the picture was very different. The distribution here of the displacement was over between 300 and 400 meters wide. And in the Dongli school, we identified probably 30 discontinuous strands. They ranged between 5 and 80 meters long. Now, we didn't go one by one. We also had the drone do the survey for us. So we did a lot of that from the imagery. Dongli, this location here lies on the hanging wall of the geomorphic scarp. Now, the interesting part in that conversation is that there actually are two hanging walls, right? Because one right? The longitudinal valley fault dips east, and the central range fault dips west, and they move in opposite directions. So you end up basically, it took me a while to understand that. Hence I'm sharing, which may be obvious to everybody else, but I'm pretty excited. So, yes. So, and most of the displacement that we saw here was reverse. The small strands was reverse, and it showed pure shortening, as opposed to the fully displacement that was left lateral. So you can see in these cases, and these expressions of the reverse displacement are aligned with the direction of the longitudinal valley fault. The same here. And if this scarp right here at 40 degrees angle, if you look on the opposite direction, it crossed the street and it cracked the foundation, and it manifested all the way to the roof of the structure. And the assumption being that the structure was relatively easy to crack, otherwise the fault would have picked an easier way to go around it. We saw, of interest to us was how sensitive the manifestation of the fault was to the geometry of the slip, the geometry of the strike. I apologize. So in this case, back to fully, as long as we were in this location, this was the cross section of the road 23. As long as we were in this location, the manifestation was strike slip. Once we turned and there was an the apparent bend, then we were right here, and then we went 30 meters down the street. And the manifestation is completely different. There's cracking and there's angles. So there's not necessarily a straightforward way to express to describe this. Even if the overall deformation of the fault is strike slip, small accommodations of the direction change of the fault manifested in very different ways in terms of its effects on the built environment. And we saw that already. And the last one was both in Fully and in Yuli, we saw repeated historical ruptures. In fact, in Yuli, the rupture is almost identical to the rupture that was identified in the 2007 paper, but by Bruce Xu, revisiting the 1951 event. The rupture is almost purely strike slip, as shown up here. I think this is an excerpt, from Bruce's paper. And the displacement is almost entirely strike slip, with an exception of a few locations where we had basically shear cracks that manifested as when they cross the track that has a lot of tension, strength manifests as an echelon type tension cracks. But it's basically the same story as the 1951 manifestation. Okay. So that's much about the rupture complexity, that it accommodated the oblique strain with very sensitive to the fault strike. that the fault knows where to go, and it picks the easiest way to get there, that the displacements were dynamically triggered on the longitudinal valley fault, and that it re-ruptured the same places in the same ways in Fully and in Yuli, similar to the 1951 sequence. As I said, one of the things that we wanted to look at was the effect of those strong motions that were within the few kilometers away from the fault. The ground motions that we got access to were processed using standard procedures of the US ground motion modeling database building. And although we do have work in progress to improve upon these as well, good grief, seriously? I'm going to do this really fast. So this is where those ground motions lie relative to the rest of the database. Can I get a little more time just to show you pictures? No, I'm kidding, no. So the ground motions were corrected for tilt in order for us to be able to extract the permanent displacements. And as you can see, for example, there was I think Director Chu showed examples about being 3.5 kilometers away from the rupture, and how there was an equal displacement in the east and in the north at one station. In a different location, you can clearly see the velocity pulses, especially as we move to the north, and the corresponding velocity. Here, the displacement in one direction is almost zero. This is close to the fault parallel, and the fault normal direction is non-zero and accommodating the permanent slip. And the exciting part about this event is that there were a lot of permanent stations of high-rate GPS stations. So we were able to actually compare the results of our permanent slip in the horizontal direction and the vertical direction with the permanent stations to confirm the results that we derived. And the results were very promising. So the strong motion stations are the orange arrows, and the rest are the estimations from the permanent stations from the high rate. And not only they agree in direction as well as magnitude, they were independently computed, so we didn't use them as a prior to try to correct for the displacement. One thing to note is this. You can see the central range fault here. The maximum displacement is horizontal is about a meter, moving in strike-slip direction, and the longitudinal valley fault has a northeast direction displacement, but you go 35 kilometers away and you still have 34 centimeters of displacement. And in the vertical direction is similar. So these are very encouraging results, because we can at least now slowly establish the methodology we tend to develop and be confident that, how much do I have? 2 seconds. One thing we've been thinking, or I've been thinking, is if the ground motions that were recorded on the hanging wall of the longitudinal valley were dynamically triggered on the longitudinal valley fault, which one is the correct R rupture to use? If the cause of the fault is the Central Valley fault, but then it dynamically triggers a different fault, isn't that the right fault to? Like, how do you accommodate for a, how do you compare to ground motion models when you have a fault that dynamically triggers another one?
Do you want an answer?
Yeah. Yeah.
The way we do it is we would run both of those, both scenarios, and we SRSS the ground motions from the two. That's what we're doing in practice for that kind of essentially multi-event rupture, right? With the idea that they're overlapping in time, and so your ground motion is a combination of the two.
Or at least, if especially it's clear that they were triggered dynamically after a certain point, could you do that for part of the fault and not for the rest?
Yes.
Yeah, okay. Okay. So far, oh, good grief. Good. So these results are not done with this approach, because I thought about this morning, and Greg said, ask Norm, and I asked Norm. So I'll tell Greg tomorrow. But, but the point is that we're still using the finite fault and not the finite rupture. And potentially we should be using the results from the Nature paper that came out 6 days ago. So I'm going to go ask Professor Ma after this presentation. So I'm learning more as I'm speaking to you. So the rest of the presentation is look at those velocity pulses and how they affect the bridges and how we use the bridges. We're building models of the bridges and shaking them with the pulses. And I'm so sorry, I ran late. And it's fascinating to have two faults that talk to each other. And how do you do hazard over time? Accounts for the moment budget. Thank you for your patience. Sorry, yeah, thanks.